optical microscope, then, okay, I agree it is being recorded. An electron microscope is conceptually very similar, although the details are completely different. But we have a column, we have at one of the ends of the column, we have a source of electrons instead of photons. Electrons travel through that column, they reach the specimen, and then through an objective lens, they form an image. This is actually what you have here. And it is conceptually similar to the optical microscope, the classical optical microscope. The big difference is that we are using electrons, so electrons have a very small wavelength, something like 1,000 times less than an atom. So certainly we are not limited by the wavelength of the radiation we are using, as it can be the case in a number of optical techniques. Then electrons get scattered with almost anything. So really all this column is in vacuum. And then the specimen is here. And as opposed to the way you see images that normally there is a reflection, and then it is this reflected light that comes to your eyes, you are going to see that the way to make the images that we are going to work with is by going through the specimen. And going through the specimen, we get an understanding of the complete three-dimensional structure of the specimen. Understand that we are talking of electrons. And probably many of you are coming from the X-ray field. So in electron microscopy, we are using negatively charged particles. In X-ray diffraction, you are using photons. So when we are using electrons, we are going to see electrostatic fields. And whatever we are going to get information about is electrostatic potential, which is not exactly the same as electron density. That is what you measure in X-ray diffraction. However, the differences are minute, and you have to go to beyond 2 angstrom to really start seeing this effect. But just have them in mind, because things are a little bit different. How the images are formed? Well, also simple optics. We have an electron beam. The electron beam, part of the beam doesn't even feel that there is a specimen here. It goes through the specimen and is scattered. Part of the beam is scattered, it forms an angle, then the optical path is, there are some objective lens here to make this electron to be focused here. And so you see that there is a difference of optical path of electron path. And then there is a difference in phase in the electron that goes through these two paths. And this is the phase contrast that we are getting. Is rather low contrast. You are going to see, really it's difficult to see the specimen, and the images are extremely noisy. So everything we are going to do is always from the rationale of working with a lot of noise. This is the weak phase object approximation, and essentially is that if we have an electron that is encountering a electrostatic field, the total number that is going to be deposited when you make the measurement in the image is proportional to the Coulomb potential along the line of the electron. It's a line integral of the Coulomb potential of the specimen. And this is very, very interesting, because suddenly these things of weak phase object, electron microscope as something with a wavelength very small, doesn't seem to be simple to understand, but just come out to be very simple to understand, because we are all used to radiographies. And even if the physics involved is completely different, the mathematics involved in many aspects of biomedical imaging with X-rays are very similar to the electron microscopy field. So an image in electron microscopy is exactly the same than an X-ray radiography. It's a projection of the specimen, is a human body, along the direction of the beam. And then it is, you see here, is the lateral of the chest. Is really very difficult to understand this image, unless in the case of radiology, you have a lot of prior information that is the anatomy of the human being. But you are having now a macromolecule, and you don't know anything, and then it is very difficult to understand these projection images. And the way to get around that problem, that is essentially that we are having information of a two-dimensional nature when we have a specimen that is of a three-dimensional nature, we are never happy with that. And in biomedical imaging, what we do is we put the specimen into a CT scanner, and the CT scanner has to do something simple. That is, okay, if with one image is not enough, I'm going to take a number of images and I'm going to go around the specimen. Well, in our case, this specimen is our microscopical sample, which is very precious, but the electron microscope is probably more precious. So the sample is going to be tilted or rotated, and the microscope is going to be kept still. But we, of course, want to have the 3D scan. We want to have a objective, quantitative understanding of the Coulomb potential, from which we will be able to derive the atomic model when we get to a sufficiently high resolution. We are going to use what is called tomography principle. The tomography principles were stated more than a century ago, and they say, listen, from one image, you cannot get a 3D object. Even if the image is known to be a projection, you cannot get a 3D object. However, if you have a set of images at different viewing angles, projection angles, then you can go back, and we have a number of algorithms to do this way back from the set of images to do to obtain in a quantitative manner the 3D structure, the 3D Coulomb potential, and from there the atomic model of the structure. This is the practical way we achieve it. Is each of these blue things are supposed to be a macromolecule, and they are embedded into a solid slab of ice, of amorphous ice, an ice that doesn't have a crystalline structure, it doesn't have edges, it doesn't harm the specimen. It has been shown that preserve the specimen to the highest resolution we have been able to achieve, that is something in the order of 115 Armstrong. So quite high, not as high as some cases in X-ray. But anyway, we have the specimens here, and we have the electrons coming here. And now we are going to make a conceptual jump. The tomography principle is this: you have one object and you get images in different projection directions. Well, when you have a purified sample, then containing many macromolecules, then each of the macromolecule is in a relative different conformation and different orientation. And then the fact that you have the beam fixed, but the macromolecule is in different orientation, is the equivalent of having different projection directions. This allows me to say that I'm going to make a point in terms of development in which I am involved in the area of purified specimens, perhaps closest to those of you working the X-ray, the macromolecular crystallography field, is that we make a certain purification, and then we have macromolecules in a defined state or in a number of defined states, and we are going to study these macromolecules, the aim being to have an atomic structure of these macromolecules. One important point, 2 points, is one is that this is perhaps the main trend right now, is the the Nobel Prize 2017, but there is a huge trend that is still cumbersome, but is there, that is cellular tomography. That is, this process of purification, of enrichment, of anything is a perturbation. Really, what you are looking after the purification certainly is related to what was there in many ways, but maybe you are forming some complexes that didn't exist. Maybe you are missing many complexes that did exist. Certainly, you do not know the relationship between complexes because you purify A or you purify B or C, but not everything at the same time. So is the area of tomography that is perhaps the next frontier, big frontier in the field of CryoEM, and we are also working in that part. But today I will concentrate, thinking that many of you would be coming from other technologies in the part that is called single particle analysis, when you have a purified specimen and then you want to study the structure of that specimen. Understand something very important is that these specimens are free to move, so they have relative orientation, but also we are not constraining them through the forces of a crystal or anything like that. So if they have a certain dynamics, a certain flexibility, we take minutes to prepare the sample. So of course, the macromolecule is going to explore its conformational landscape. And once you freeze it, it is frozen, and then it doesn't move. It doesn't move. And you have captured whatever is the state there. But before being frozen, it had been moving, so you have the capacity to study and this is what we are doing, the capacity to study the flexibility of the macromolecule, and to do that on a time scale. Time is still important, in the range of the milliseconds. Okay, so because this is the time that takes to freeze, so you cannot go faster by this technology. There are other technologies around. You could go to the microseconds, but in very special cases. When you hear time in the context of electron microscopy, you should translate it into milliseconds. And this is a promotional video. Sorry to put a promotional video, but it's interesting. You have there a lot of macromolecules purified. They are frozen at minus 180. There is already fast frozen. You stop crystallinity in the ice, and now you use the electron, you get the projection images. This is how noisy our images are, and then we select a number could be 500,000 particles there. We a posteriori detect the projection direction, and once we know the projection directions, then we do the 3D reconstruction, because we start using this algorithm that were started to be proposed 110 years ago. And we are able at the end, through reprojection, to get an estimation of the Planck potential. And if you get higher than 4 Angstrom, 3 Angstrom something, you can confidently start making a model. Now, the situation is that we have many specimens. I mean, right now, electron microscopy is solving structures is the fastest growing technology. So really, all technologies are needed because they are looking at different things. But really, in terms of getting structures with a molecular weight starting we can go to 40, 50 kilodalton, but really we are comfortable starting in 100 something kilodalton. And there right now is very common to get 3 point something Angstrom resolution. In 5 years, I probably would be telling you that it's very common to reach 2 point something Angstrom resolution, and at the same time to get dynamics of the system. At this point, we are working on that with very interesting facts. So this is the recapitulation. We can really, and this is what I'm going to present you in terms of research, to study the flexibility of these molecular machines in solution. And well, you have here a number of structures and really how they move. This is there are three systems. The ribosome has changed from being the system in which we were developing everything in the 70s, 80s, myself, to being, well, still a system in which everything is developed and is very big. Everything before it was not relatively felt. So this, of course, you know very well, is the spike of SARS-CoV-2, and this would be one of the case studies, but probably the deepest case study we go through. And we are also working in factor HER2 and the flexibility, the huge flexibility that protein. Well, when did we start doing things like that of classification? You have a collection of images coming from a collection of macromolecules. You certainly cannot think that all of them are exactly the same, that there is no flexibility in the system. Normally, there is going to be flexibility. I am hesitant to say dynamic because the time information is not that easily captured. Okay, so, but this is one of the, well, probably this is the first case, the first study in which we were able, working with Joachim Frank, in making 3D classification and 3D class analysis with negative stain, which increased the signal-to-noise ratio a lot. And, well, we were able to do it in a simplified manner, and certainly for hundreds of macromolecules, and with all the problems of a hierarchical ascendant classification and things like that. And then the field waited easily 20 years until we developed something else. And we developed something that has been commented before, is with the cryo images, with images that were no longer negative stain, images whose noise was between 100 and 1,000 times more than the signal that they contain. We were able to simultaneously finding the orientation, the relative orientation between the particles, and putting or classifying the different macromolecules into different states. Of course, this was 2007. At that time, we had to make an important assumption, was that the variability that your specimen had to be of the form that there were a number of stable states, number of classes, and that you had to know this number of classes as a parameter. We were not happy, but we didn't know how to do better. So this K number of classes has also always been very controversial, and people have tried with different cases. The goal, in very simple terms, what about if we take away this assumption? What about if we no longer think or impose on the data that something that they may not be proper for those data, is that they exist as discrete set of state, and I am to use the number of state as a parameter of the alignment classification. And now we are in the field of conformational variability. We are there, but we are not the single people working here. It's a crowded, perhaps 3 or 4, a little bit more perhaps, groups in the world, and we are aiming, Joachim included, of course, we are aiming the same, is we have classes, or we have states that are mixtures. We would like not to have this mixture. We would like, in a mixture, it happened to things. One is that by definition, you get a blurry. We don't want to get a blurry. And the second thing that happened is that you lose information of the flexibility of that macromolecule. So you get a blur, while what you would really like to have is a continuous that tells you, well, is that this macromolecule is moving this way. And this is the path of movement of this structure. And so it is as if you, for those of you that are more close to SARS-CoV-2 spike, the spike is characterized with a huge flexibility in this area. It is the receptor binding domain. And to say that it is up and down is to say that from a potentially rich conformational landscape, we are just taking 2 points. Well, the reality is a little bit more complex. So we would like to get to that. We would like to really be able to follow paths. We would like to have information on less stable conformation that, however, would be key to understand the dynamics. And of course, we would like to relate all that to molecular dynamics. That we are heavily working there, but yet we are not there. So we want to address the continuous flexibility without discrete classes, and we want to do that because we want to take subtle changes. We want to decrease the blurring in the images due to movement, and also at the end of the day, we develop methods, and we know that if you impose assumptions that are not fulfilled, I mean, if I insist that the data have to be of a certain class and the data are not of that certain class, then I'm going to decrease the stability of reality. So one of the points in my mind was always to use the hypotheses about the data, about the processes, about that really are pertinent to the data or to the processes. Sometimes you have to put more, but you don't know how to do. You don't put this, but this always, you will pay something. Of course, this is going to be complex. We want to explore in a reduced dimensionality way and really increase the capability of deblurring the images from a blur, getting a complete set of different structures. And part of my work is really in the field of European infrastructure. So one of my responsibilities is that these developments are accessible to people. So the programs might exist, the environment for computation have to exist, and it should be easy to use, and we should make training of the people, courses, and all that. So this is a facet that we will be also introducing at the end of the. Let me present you how we approach, and which is also interesting in terms of how in 4 or 5 years this subfield of flexibility has progressed. We started with principal component analysis. Probably all of you know principal component analysis, and you are used to having data of dimensionality n, and in this dimensionality n space, you calculate principal component, and you see the main trends of variability. Perfect. It's not our case. We have images, which are 2D. And from the 2D images, we have to infer the principal component analysis in 3D of the space of maps, the space of volumes. So it was less obvious than what you think, but it was anyway the first approach that we did. And we went beginning of the pandemic, beginning of 2020, this was the first structure that was published, and immediately we got in touch with this group, Jason McLellan, and we got the images, and with the images, we were able to perform this from the images, from the 2D images going to the 3D volumes. and obtain the principal components, we were able to see that the closed and the open space were really two states, but there were many more before, many more additionally. However, principal component analysis, being a linear technique, it has also a number of limitations. So we had a nice cloud. We saw that there was more than close and down, up and down, but to be quantitative was more difficult. The streams of PCA, it was clear that it was a movement, NTP, RPT, and really it was concerted movements. Then we went so many variants with so many mutation, and really the effect, the allosteric effect of mutation and all that. This is a very interesting field. But from the point of view of flexibility, I wanted to convey to you how we move very quickly with images and with the tools we had in the moment. I thought we had to do it. That was 2020. And we presented the first data on the flexibility we were seeing in the images. Then we started to develop other methods. And really, the field right now divides into two types of method. One is deformation field-based method, and the other are called density-based methods. The deformation field is the following. Listen, I'm not interested in those cases. I'm not interested. Is that my methodology is not going to work for those cases? I'm interested in those cases in which the macromolecule has a defined composition. We are not talking of a compositional heterogeneity. We are talking that the map is flexible, and I may work in atomic resolution. Most often, I will not be working on atomic resolution. I want to know how the images tell me that the average structure of my data set should be deformed to produce the specific images I am obtaining experimentally. So there are a number of methods here. The first one probably was normal mode analysis. 3D flex, you may know, because CryoSpark is very well known. Works very well. 3D flex is one of these methods. And our approach is based in a certain polynomial base called thermic 3D. That essentially is simple. What we did was to express the variability or the variation that happened into a volume through coefficient in a certain base that had a number of interesting properties. And then we were just saying, listen, we have a projection of the volume, and here we have the volume with the deformation. We want that this, once projected, would be very similar to the image that we get. Is exactly that. You have the reference map, we call it, that is the average, the blurred average of your data set. We are now, I want to calculate a thermic, a 3D deformation field for each of the images. So you are getting 1 billion images and getting 1 million fields. I deformed 1 million times this reference volume. I get a deformed volume that I project, and then put the CTF, whatever, and then I so make the projection as realistic as possible, and then I compare to the experimental practice. This is essentially the idea that we had, and we started with optimizations, and then deep learning and all that dominated everywhere. And everything we do now, of course, is AI-based deep learning. So essentially, this is the type of thing that we can do. So with the case of the ribosome, that is a nice big case. You see this rotation of the 40S on the 60S coming from 2 points of the landscape. So each of these points is an image. And what we are seeing is that we can map the conformational space that is being obtained through the images of that specimen, we have this reduced representation. We can explore this representation interactively. That's what we want. And we get information about the flexibility. We do not get information about the dynamics, okay, in terms of time, because the specimen had the time to explore its conformational landscape, but they were frozen in a certain moment. And it took milliseconds, the freezing. I cannot do more. But so this is exactly the same. And then this is an interesting example is the case of HER2 with a therapeutic antibody, and we were able to get the images of HER2 to go to conformational landscape, to select a number of points in that conformational space, to get reconstruction out of them. And we were able to see that there was certainly a flexibility in the macromolecules, a flexibility in the area where the antibody bound. Trastuzumab is a therapeutic antibody, but also in the area where the dimerization bridge with other herds is. We were able to prove unambiguously that the sample with trastuzumab and the sample without trastuzumab were very different in terms of the flexibility that it had. Really, there is a change, a compactation when the antibody is put in the mixture, and also the range of opening and closes is different than the much more stable case of the HER2 without anything. And from there, we were able to say a number of things. For instance, really, this is the structures coming from the X-ray script from the electron microscopy complex of HER3 and HER2 when they complex. Well, we have seen that with trastuzumab, this HER2 gets compacted. So the dimerization arm of HER3 is not able any longer to get into HER2. So we may see an allosteric change produced by something over here, by the antibody here, that translates into a closing of this ridge, and through that, a therapeutic effect in avoiding the formation of heterodimers or other types of dimers. Let me finish with density-based approximation that are probably where we are working the most. Again, there are other fields, other methods. CryoDragon in this context is very strong. They were the first going into seriously AI and working in the area of conformational variability. We have been making changes, many changes over there, but still it is very used and very good method. And the notion behind this density-based method is really what seems to be a dream, at the same time a nonsense. And it's the following. We have to do the classes, and from there we have to do the 3D reconstruction. This is the normal procedure we have been telling you, the normal procedure we have been following for the last 30 years, one way or another. I mean, would we be able to get a reconstruction from each of the particles, each of the images that are in the data set? Maybe thinking impossible, of course, because you have to the information. We have seen before that this would be a radiography, so no way to get a 3D reconstruction. And I'm not going to claim that this is possible. What I'm going to say is that we are able to get the information from that image and non-linearly the information from many other images and combine them in a way that indeed for each of the images for each of the specimens in each of the images, we are able to get a decoded map, an artificial, synthetic decoded map up to high resolution. This is what we are doing now with HET-Sealing. Is our latest baby in this thing. Is we are extremely happy. Allows you to do full focus reconstruction, so it allows you to put a mask and to just study whatever part you are interested in. It has many things related to sharpening, denoising, and also we are doing something that is extremely important. It's for the first time, that is disentanglement of projection, direction, and classification, meaning that depending on where you are looking at the macromolecule, it belongs to a certain class, maybe obvious, maybe less obvious, or maybe doubtful. So we wanted to take all that information at once and consider all the information about all possible directions in the ability to go to latent space, to conformational space, and present you a certain one. So I'm not going to get into this. I mean, really, we are able to study that set and get identify states that were not possible before, and with a higher resolution. We can do that in the landscape to go through the maps. You see how the local resolution really it's improved substantially. So you are seeing in a way the next generation of methods. Of course, we are now also using that for alignment. So we get alignment information at the same time that we get information on flexibility. This is work with Siran Subramanian on the spike with different strains, and understanding really how all the complications of analyzing the data and classifying the data, much of that is really taken away by this process. And this is something I am very proud of, is since we are able to know, and coming back to the techniques, since we are able to know how much you have deformed, you have to deform a reference map to account for the image you are seeing. Could you now think in a way to make a reconstruction that would be different, that would take into account the conformational variability, and that would produce one map, several maps along the trajectory, but each of them considering different images with different deformations? Yes, absolutely. We are able, and the results are coming out. The way we do that, for 45 minutes, I'm going to go fast, but not much. I don't go into the details, but really the result, it depends a lot on the data set, okay? But for many of them, the unblurring is substantial. Unblurring and getting a better local resolution. The link to molecular dynamics is something we are working with. Is not easy. And then I finalize with this point on infrastructure. You remember I was telling you, I am responsible for the instruct image processing center. So it is great to have advanced mathematics, but at the end of the day, we need this method to be used by people that are not method development. And when you have in front of you a number of network architectures, and you see that you have the parameter of you don't understand what is A or B or C. So we have created an environment, CPM Flexibility Hub, where you can really study, work with a number of algorithms and compare the strength and weakness on the specific cases that come to this I2PC center as part of the Instruct ERIC initiative in Europe that I understand is also getting in contact with a number of actors in Africa as well. Is an Instruct service, so it is in Europe at this moment you can apply for your images to be studied at the I2PC with you in the context of the Flexibility Hub service, and we certainly do courses. This was the first course, June last year. In June this year, we have made the second course, Flexibility Analysis, and this is open to the world. So if you have any of these problems that that have been a bottleneck for many systems, and at the same time, it's fantastic source of information. So this is where the connection with biophysics, that's where we want to go. But okay, this is really the team. David Herreros is the brilliant predoc and postdoc that has made a lot of work in the conformation variability. James Krieger, molecular dynamics, electron microscopy. Carlos Oscar Sanchez Sorstano is the co-PI in the lab. And with that, I'm thanking everybody who has given us some money. I would stop and I would be open to question 1 minute past my time. Thank you.
Thank you, Jose Maria. That was extraordinarily interesting, actually. I mean, the flexibility of biomolecules and the implications for their biological behavior is profound, and being able to analyze it in the microscope is clearly the way to go. I think I'm going to ask other people to ask questions before I do. I have several. Does anybody want to put up their hand for questions? Can I see?
Don't be shy.
Don't be shy, yeah.
I have one.
Go on, Lawrence.
What are some other types of molecular applications that you could try to apply this to? Sort of industrial polymers and brushes and things like that. What are
to be honest, we haven't done it. We have not even considered them, but it's a shortcoming from our side.
Yeah. Okay.
The whole business of CryoEM in biomolecules depends on each molecule being almost identical. And this is generally not the case in polymers.
I see. Okay.
Okay. So the things that I wanted to talk about. Has anybody, to your knowledge, studied the details of substrate binding and the relationship between the flexibility of the molecules and the activity of the molecules?
Well, people have worked with receptors, with membrane receptors. Polymeric, you need a mass, you need to have 100 something. And a case in which certainly I should mention that strongly, because it was the first case, was one of the ryanodine receptors. And it was the work of Joachim and Maria de George. And they did an analysis of conformations in the apoform and with a number of substrates, and they analyze it with a different mathematical approach that I haven't covered here, but with the flexibility in mind. And they were able to see the transitions that were happening, and they were also able And that was interesting. They were able to see how the transitions that they saw when making a fully continuous variability analysis and when making a cluster-based approach were different. I mean, that the stability of the algorithm for making a classification, when the data do not have clear states, they are going to give you something somewhere. And you cannot take for granted that this is the state that is going to define your transition. It's just one of the possible states. And next time you run the algorithm, it will be something a little bit different if you do not have this cluster structure. So when you have very stable classes, it's everything very clear. So they were able to show that. They were able to show meaningful differences when making this type of analysis and when making a 3D classification that we now refer to it as discrete classification as opposed to continuous classification.
Okay, that's very interesting. I want to make a general comment about CryoEM in Africa. So there are a whole lot of issues with African people getting access to microscopes. And although we've been a member of Instruct for several years now, very few people outside of my direct group have made any use of Instruct facilities. How do you think we should expand the use of cryomicroscopy? And do you think that we should have perhaps Instruct courses in Africa?
Yes, I mean, we are doing that in South America. I mean, I coordinate. You know very well that Instruct has worked with South America and with Africa. South America, I am in charge of it in the sense that I coordinate the program, they coordinate the project that is about advancing research infrastructures in the EU-LAC region. And we are doing we are having with us people for months or sometimes for years from facilities there. That's important. Instruct is about infrastructures. So we are talking about facilities and training the people of the facilities. So another thing is then the researchers. So for the training of the people, we are doing courses and stays between 1 month and 1 year and a half. And about courses, yes, I mean, this could be done in other locations. At this moment, we are exploring, this year it will be twice, with the facility course that we have in November and with the tomography course that we have in tomography. I think for you this is not an issue, but for America it's an issue, the time frame. So we are going to do everything in the afternoon, evening, night, so that we could be together. I understand that it is the same time frame or very similar, Cape Town and Madrid. So.
And you do know that there's not a single Glacios or a Krios microscope in Africa.
Yeah.
So accessing the infrastructure to get specimens to these microscopes in Europe is difficult.
I mean, something that we are working in South America, Trevor, is the way to send a specimen, to have a sort of intergovernmental a special situation for sample, because at this moment there is no guarantee that you do not lose the specimen sending it anywhere.
And what about the computing facilities, Jose Maria? Can people apply to use the computing facilities in Madrid?
Well, at this, we had it that at the beginning. It was purely on the cloud effort. We don't do it now because it was very difficult to convey the things with the research. We really wanted that person to be able to do it next time, because it's not going to be your single data set. You are going to be producing data set, and the point is to be trained through research, and that not always do the same thing. So you are supposed to do things at home. Also, really, right now it is easy to do what you are saying, and we do that for all courses. All courses we have given in India, in China, of course in South and North America. Everything is run on the Amazon cloud. Everybody has its own machine. And the virtualization of capabilities is enormous.
Yeah.
It's a matter of money at the end.
That's very good. Yes, that is also possible here. Okay, any other questions? I think there's been one or two compliments that have been in the chats, but no questions at the moment.
I do have a question.
Just one question.
Okay, go ahead. Go ahead, Jimmy.
Probably to follow up with your question is, are there any opportunities to collaborate? We do have here in the US a lot of small institutions that don't have the capabilities and training to do CryoEM, but they're very interested in. And so we do have these national centers that we use, but we also found that it's not really democratized because there are distinct barriers for each institution, and these barriers can differ across institutions. And so one of the, like for us, not having an opportunity to make grids or freeze grids has been a challenge. And so that's where we're starting. We're also learning that protein sample prep is also a challenge. So I've been interested in trying to understand what collaborations we can develop or pursue to make it more accessible, whether it be from the sample prep, the wet bench, or just the computation and the data processing angle.
No, I don't think that is the data processing angle only. It is common that when people come to us with the first images, after some short processing, the advice is go back to the bench. Go back to the bench. We are seeing that there are these problems in the sample, or try to follow other guidelines. You talk about the freezing capabilities, and this is true. I mean, at the same time, we have not found that to have freezing capabilities without some way to check the images makes much sense, to be honest. I mean, you have to have somehow around the capability to check the bits. We are doing that you are saying that there is no that type of microscopy in Africa. In South America, except of Brazil, which has several, there is no other microscope. However, there are fantastic scientific communities in a number of countries, and what we are organizing are ways to first go to negative stain, understand negative stain, because this is what you would do in a normal lab. You would go first to normal, to negative stain, you would check that. Once you are there, you start thinking about going into cryo. But I think that we have considered the whole process, and the whole process starts earlier than what sometimes we think, and certainly not. I mean, for a set of people, for perhaps this special thing of flexibility, yes, it starts with the set of finishes. They have done many things in the past. They are at this moment with a problem that is complex and new methods, complicated methods. Perfect. But for many others, things are more basic, and they have to go back to have some capability close of checking the sun.
Thank you, Jose Maria. I think I'm going to close the meeting now, seeing that there are no further questions. And thank you very much again for taking the trouble to come and talk to us. It was most enjoyable, especially for me. Thank you.
Thank you very much, Trevor, and everybody. Thank you. Bye.
Thank you, Jose Maria.